guys, it's Mrs. Warner here. We're going to start a new chapter, chapter 3. I can't wait. We have 12 chapters total in geometry, and we're making it to chapter 3. Today we're going to do some symmetries and some rigid motions. That means we're going to look at things like reflections, translations, some rotations, and we're going to check those out. Okay, so the first thing we'll start off with is some line symmetry. You've probably seen this before, but if you can reflect a figure over a line and its image maps onto itself, then that figure has some line symmetry. So there's a couple examples down below here. There's the letter A, and I drew in this line of symmetry that is vertical because if you folded the A on that line of symmetry that's vertical, the A, each vertice would map onto itself. So the corner here would map onto itself over here. This would map to here. Usually a line of symmetry is drawn dotted. In this angle down below, the line of symmetry goes through the middle. My drawing's kind of like, crooked, but that would go through the middle of there. And again, each vertice would map onto itself on there. And another name for the line of symmetry is the line of symmetry is generally a perpendicular bisector of the image. So each point is equidistant, and that line is drawn perpendicular. Like if I drew a line that connected these endpoints up here. Wow, do you see that with my mouse? That was great. These endpoints will be bisected, so this line bisects them. So each piece is equidistant to that line of symmetry, and it actually meets at a right angle in the picture there. So it's a perpendicular bisector, that line of symmetry. Okay, line symmetry is a line that you could draw on a figure and it would map it onto itself. Can there be more than one line of symmetry? Absolutely. We'll see that in a few examples as we get going. Okay, rotational symmetry. Now, rotational symmetry, if there's a center point, which the object can turn about a certain number of degrees, and the object is going to look like an image of itself. So if you look down at these shapes down below, this shape's a parallelogram, and this shape is a triangle. If there's a center point on those shapes, and you could rotate that triangle or rotate that parallelogram around or turn it so that it actually looks like itself again, then it has rotational symmetry. Very exciting. Rotational symmetry is different than point symmetry, which we'll talk about in a second. Okay. So they're two separate things, rotational and point. In this case, these both have rotational symmetry, and you'll see why. There's something called the order of symmetry. Super important word. Order of symmetry is the number of positions in which the object looks the same. So in other words, it's how many times you can turn the figure and it's still going to look like itself. So if we took this parallelogram and turned it around, it actually has an order of 2. So maybe we should make a note down here that this guy has an order of 2. If you turn it upside down, that's one turn, and then you rotate it back to itself, that's another turn. So it has an order of 2 for this parallelogram. However, this nice little equilateral triangle over here has an order of, I can't even type. Look at me type. That's fun. It has an order of 3. Okay, so it has an order of 3 because it could take 3 turns, and each time it turns those 3 times, it looks like itself. Order is how many times it can turn and look like itself. Now, the angle of rotation is how many degrees you have to make that turn so that the figure looks like itself. Now, to figure that out, there's a nice little formula. If you're taking a turn, you're going to go 360 degrees. So if you do 360 divided by the order, so for example, on this guy here, 360 divided by 2 means 180 degrees is the angle of rotation on this figure. Likewise here, if you did 360, oh look, my picture's there. 360 divided by 3, then 120 is the order of our angle of rotation there. Because 3 was the order on that shape. It's confusing. Order is the number of turns it takes. The degree or angle of rotation, you take 360 and divide it by the order. Oh, that was fun. Okay, now that's rotational symmetry. Point symmetry is totally different. Point symmetry is, oh God, it's so sensitive on here. So point symmetry is when every point has a matching point that is equidistant from the center, but in the opposite, I think that's supposed to say direction on there. So for example, if you rotate the figure 180 degrees and the image and the pre-image look exactly the same, then it has point symmetry. So you know what I would do is if you're given a shape and it's a test, quiz, homework, or whatever, to tell if the thing has point symmetry, you simply take your paper, rotate it 180 degrees upside down. Does the shape look exactly the same? Yes, it has point symmetry. Different than rotational symmetry, because rotational can go at different angles. But point symmetry has to go upside down in order to look the same. Okay. Now, this next stuff is super duper important. So maybe star it on your notes, because this definition of what a congruence transformation or a rigid motion is going to have to get memorized. A rigid motion, rigid means it's not going to change size, okay, and motion is some sort of movement. A rigid motion is a transformation that preserves distance and angle measure. Okay, so there might be questions that ask you, is this transformation a rigid motion? And you're going to say yes. A rigid motion preserves distance and angle measure. You're going to write that out exactly as it is, word for word. Okay. Another word for a rigid motion might be something fun called an isometry. Isometry also means it's not going to change its size or shape, or its distance and angle measure don't change. Okay, super important. Those two words, distance and angle measure, are written for your explanation. So for example, if you look down here, a reflection or a flip, this is a reflection. It's flipped over this x-axis here. This reflection is an example of a rigid motion. The distance didn't change. See the side LM? And remember, when you're doing a transformation, you use the little primes. So like now it might be L. Oh God, this mouse is so terrible. L with a little prime symbol at the top. Rawr. What's happening with that mouse? Or like M. Oh boy, people, with a little prime symbol at the top. It's kind of like a, I don't know, apostrophe or something, but not really, just a single one. All right, so that's a reflection. A rotation is a turn. See how the shape has been, it was here, bam, now it's over here. It turned around, that's a rotation. And a translation, somebody just slid it, there it is. It's a slide of a figure. Angles don't change size. The lengths of the sides don't change size. Those are 3 examples of rigid motions. They make the image congruent or the same size and shape as the original one. Now, why don't we have dilation in there? That's easy. Dilation makes things bigger or smaller. Super naughty. We don't want it. Okay? Only these 3. Oh, let's think. Some properties that are preserved. I put these pictures back here just so we can look at them and see what the words mean. Distance or length. Obviously, if you look at any of these pictures here, the size of these things did not change. AB is the same size as A prime, B prime. Their lengths have not changed. Distance or length are preserved or saved under a rigid transformation. Angle measure. Ooh, angle B prime, they're the same size. Didn't change size. Parallelism, what the heck is that? See on this trapezoid here, when you reflected it, LM and ON are parallel, so are their primes. O prime, N prime the same, L prime, M prime the same. Still parallel. One's not going to go crazy and not become parallel. Collinearity, what the heck is that? If things are collinear, they stay in a straight line. So like C points L and M, that didn't change and it didn't become L and N or L and O. They're still L prime and M prime. Those points stayed on the same line. They didn't jump their position around. Collinear. Orientation, now what the heck is that? Okay, that's like this. If I were to talk about this shape here, if I were to label it, say I started at O and I went clockwise around here, that would be O, L, M, N, right? But now say I went down here to O on the bottom. Do you see now how it goes? If I start at O and go clockwise, it goes O, N, M, L. See how the order of the letters is different? That means the orientation has changed. So it is preserved on a rotation and translation, like E, F, G, H, stays E, F, G, H. But when you reflect it, it's flipped. Like think about it, like if you look in a mirror, it's actually your image that's backwards in there. Okay, so the orientation has changed. And then if things are perpendicular, they're going to stay perpendicular, like AE is perpendicular to ED. Same thing here, AE and ED, the primes are still perpendicular. Those things are preserved. Oh, fun. Okay, so let's try some examples. Let's look at number one. Oh, can we do B first? Because I already did it. Okay, so it says, are any lines of symmetry? And if so, draw them on. Oh, I drew two in. There are two lines of symmetry in the picture. Now, why do these not count? Because technically, if you folded this on this line, that D and B are not going to match each other. In a rectangle, they won't like fold up to each other. So the diagonals don't work as lines of symmetry, just vertical and horizontal on there. This question says, what's the minimum angle you could rotate it around that center point M and have it map onto itself? 180. It has an order of two rotations where it will look the same. So you take your 360, remember from our little formula, divide it by 2, and it gives you 180. That was fun. Okay, next, we've got for each shape below, determine if it has rotational symmetry. So I like to look at the shape, and if it's something called regular, okay, so regular in a shape means all sides and angles equal in measure. Right, so this shape is regular. This is a regular hexagon with the 6 sides. If I take 360, divide it by 6, because the order is 6, it has the 6 vertices, that gives me 60 degrees. So every 60 degrees, I turn that shape. That is its rotational symmetry. Let's look at this guy down here. Oh, this is not a regular shape, but it still has rotational symmetry because it has an order of 2. If you turn it upside down, it still looks the same, the rectangle. So 360 divided by 2 is 180 degrees for its rotational symmetry. We have one last example down here, a little multiple choice. It says, here's our regular pentagon. Which of the following angles of rotation around center point O would not, make sure you read these questions carefully, would not carry the figure onto itself? Well, since it has 5 vertices of the pentagon, I take 360 divided by 5, that gives me 72. 72 is a choice, but remember, I want which one not carry it. So I'm going to take 72, I'm going to look for all the multiples of that, of 72, that should say. So if I do 72 times 2, that's 144. There it is. Yes, that works. 72 times 3, 216. Not in the list. 72 times 4, 288. There it is in the list. This 224 is not a multiple of 72, so it's bad. Okay, all sorts of stuff. Line reflections, point symmetry, rotational symmetry. What is a rigid motion? Remember, rigid motions preserve distance and angle measure, and they are things like reflections, translations, and rotations. People, that was fun. I hope you had a great time taking your notes. Don't forget to do your homework and have a fantastic